Okay, so I want to talk now about what it means to find a solution to a differential equation. We've talked in the last video in 1.1 about what a differential equation is. What does it mean to solve a differential equation? Okay, so recall that a differential equation is simply an equation involving derivatives, okay? And derivatives we interpret as the instantaneous rate of change of quantities, okay? And I gave you some examples of what are called ordinary differential equations. That might be something like Newton's second law, an ordinary differential equation, or radioactive decay. And I also gave you examples of partial differential equations. This might be, for example, the heat equation, which when your quantity of interest, in this case heat, U, is depends on more than one variable. Okay, but what does it mean to solve a differential equation? Okay, so that's going to be my next topic here. And before I get there, let me ask maybe a smaller question. What is a solution? To a differential equation? It's a good question. So here is the answer that the key thing here is that it's a function, which, when substituted into the dE, satisfies the equation. Okay, so let me clarify what I mean by this, perhaps through an example. I think this is probably the best way of going about it. So let's look at an example of a differential equation. And rather than try to justify the importance of this equation using some kind of physical example, I'm just going to write down a differential equation. Okay, here's an example of me just writing down a differential equation. Y prime equals ky. Here's a differential equation. This is an ordinary differential equation because we're implicitly assuming here that y depends only on one quantity. We'll call that quantity x, okay? And what I want to say is, for this equation, y equals e to the kx is a solution. Y equals e to the kx is a solution. Oh, I should have said, what is k here? K here is just a number. K is just a constant, okay? Y is a function. So our solutions to differential equations are going to be functions, right? This is very, very important. So they're functions. So remember back in the, like when you were in 8th grade, you might have you might be asked to solve an equation like this. 3x plus 5 equals 7. And you recall how you did that. You subtracted 5, you divided by 3, so you learned that x was equal to, I think, 2/3, right? Notice that here the solution to this algebraic equation, we call this an algebraic equation, the solution to that is a number. It's not a function, at least we don't think of it as a function, it's just a number. So differential equations are different because the solutions to differential equations, things like this, are functions now, okay? And that's the point that I'm trying to make with this red comment here, is that solutions to differential equations are functions. Now, why is this? I'm asserting, okay, that this is a solution. Why is it a solution? So why? Because what is y prime? Well, remember by the chain rule, y prime is just k times e to the kx. Remember the derivative of e to the x is itself, so the derivative of e to the kx is e to the kx times the derivative of kx. That's the chain rule bit. That times the derivative of kx, but that's the chain rule bit. And that's k, so we put that k out front. So now if I substitute y equals e to the kx and y prime equals ke, well, let me do that again, ke to the kx. If we substitute these two quantities into our original differential equation, which is right here, okay, we get, let me do this in green, y prime is ke to the kx equals k, that k that comes from right there, k times e to the kx. Oh my god, these are obviously the same. You see that, right? So in other words, I've taken these two, this expression for y, this expression for y prime, shoved them into this differential equation right here. This expression for y, this expression for y prime, shoved them into this differential equation, and I see that I get something which is obviously true. K e to the kx is equal to k e to the kx. And this is a check that, in fact, this is a solution. Important question. Is it all the solutions? Are all of the solutions represented by this expression, e to the kx, as we have here? And the answer is no. So I would say that this is, here's the way I want to say it in English, okay? Y to the kx is, and this is a crucial word here, a solution. Do you notice that that's not the word the? This is not the solution, because I'm saying, and I'm right, that there are other solutions to this differential equation. And maybe it would behoove you to just pause the video and think about what are some other solutions to this differential equation. But in any case, I won't leave you in suspense. Here are some other solutions. Maybe purple? Okay. Here's some other solutions. What if I took, oh, I'm running out of paper here. I'll just do this. Y equals c times e to the kx, where c is a constant. You can see there's lots of constants floating around in differential equations. This is going to be very typical. C is a constant. I claim that this is a solution. And again, you can check, right? Y prime is going to be k c e to the kx, and y is just c e to the kx. You can substitute these into the differential equation, and you'll see it in exactly the same way that it all works out, and it's fine, okay? And in fact, what we see in this solution is an infinite family of solutions. There's infinitely many different solutions here, okay? That's what we mean when we say that this is a solution, all right? Okay, another example. Let's make this very, very concrete, shall we? Let's say this is and by the way, can I say this y prime equals ky, this example here, is a very, very important example, one that's going to come up a lot. Okay, so it would be good for you to learn this. We'll say more about it, but this is going to be one very important example of a differential equation. Another example. Let's say that we have the differential equation y prime equals x plus 4. Okay. So this is a differential equation because it involves a derivative. Let's solve it. There. So I want you to notice that y equals 1/2 x squared plus 4x is a solution. Why? Because what's y prime? Y prime is exactly 2x plus what? No. I do know how to do calculus, okay? So just relax. The derivative of this is x, that's the whole point, and the derivative of this one is 4. Oh my gosh, which is exactly what we have here, right? Which is exactly what we've got right there. So indeed, when y is equal to 1/2 x squared plus 4, y prime is equal to x plus 4, and we get exactly a solution to this differential equation here. So that's a solution. But is it the only solution? We can ask the same question that we asked before. Is it the only solution? And the answer is no, right? There are lots of other solutions. For example, so here's some other solutions. What if we took y, instead of being simply this, y equals 1/2 x squared plus 4x. What if we modified this one to put a plus c here? Does this remind you of anything? Reminds you of Calc 2, no? Or I was being an absolute fascist about requiring you to write that plus c. Why was I so prickly about that? Well, it's because I knew you would eventually take differential equations. And here, in differential equations, this plus c is incredibly important, okay? Because this, in fact, represents a whole infinite family of solutions to this differential equation. One for every possible choice of this constant c. You can make c be 0, in which case you get this one. Or you can make it be 1, 2, 8, 8.1, square root of 8. You can make it be literally any number, and you'll also get solutions. All right? In fact, this thing here, you see this, which was this infinite family of solutions to this equation, and this thing here, which is the infinite family of solutions to this equation, these are what are known as general solutions. This is the general solution. And I haven't justified this. I haven't justified that, in fact, not only are these infinite families of solutions, for each choice of c, here and here, here and here, you get a solution to the differential equation. Not only is that the case, but in fact, every solution to this differential equation is given by something of this form. And every solution to this differential equation is given by something of this form. Okay? That's the sense in which this is a general solution. And so our goal in this class is to learn how, given a differential equation, we can find the general solution to that differential equation. That's enough for this video. See you in the next one.